Hey guys, it's Tuesday, June 2nd, 2020. My name is Noah Seeley. Welcome to my channel. So today we'll be reviewing an article that's related to machine learning. So the topic of the article is convolutional neural networks, or CNNs for short. So I'll be reviewing CNNs in related papers for the next few videos. Today's paper is a super good starting point for convolutional neural networks, and where a lot of interest in modern research for the topic started. So the paper deals with an architecture called AlexNet, but the paper itself is called ImageNet classification with deep convolutional networks. It was made by the team of Alex Krizhevsky, Ilya Sutskever, and Jeffrey E. Hinton, all from the University of Toronto. And of course, I'll have those referenced citations down below. So CNNs are a great image recognition tool, as they have much less parameters than feed-forward networks, which were previously used. Basically, a CNN is an image classifier in the realm of supervised learning. What this means is that the modern trained CNN is able to take an image as input and output a prediction of what that image may be. For example, if I use a photo of a dog as input on my little trained arbitrary CNN, it would be able to distinguish, say, whether it's a cat or a dog, and it will output that accordingly. So hopefully if it worked and was trained correctly, it would say that my input image of a dog is looking like a dog. What's even cooler about the modern CNN is they go much more advanced than just dogs and cats. Even the one we're looking at today will be able to distinguish between many images. So this paper states that the reason why a lot more CNNs are kind of plausible in today's machine learning climate is that, for one, GPUs or graphics cards or graphics processing units are much stronger than they used to be. And also training data sets are becoming much larger. This basically means that we have a lot more data to train our CNNs off of, which in turn will help them become much stronger and better at classifying input. So the data set that was used by AlexNet in this paper, for this paper, was the 2012 ImageNet competition dataset. The 2012 ImageNet contains many different images which competitors trained networks to be able to classify. This architecture basically blew its competition out of the water, and there are a few key tricks in this paper that kind of made that all possible, and I'm going to discuss them. Yeah, so basically I'm not going to talk so much about the architecture of the model itself. Maybe that will be in a later video if anybody wants it. But currently I'm just going to kind of talk about these tricks that they were able to pull off, which really helped in the training and therefore accuracy of the model. And when I say that, the kind of general term that we're going to be using is that it was able to reduce overfitting in their model. Basically, an overfit model is a model that is not trained well enough to accurately classify anything other than the data that it was trained on. A super simple example of this is that if I give you 3 math problems trying to teach you arithmetic, 1 plus 1, 2 plus 2, and 3 plus 2, if you only memorize the answers of those questions instead of trying to understand actual addition, you will get a 100% accuracy rating on those questions, which looks really good only if our math test contained only those questions. But realistically, if I gave you an addition test asking for, say, 8 plus 9, you would fail. So as machine learning engineers, it's important that we are not only teaching our models the test data, but also formulating predictions for never seen before data. So with that being said, I think we're ready to kind of dive into the key features of this paper. So the first key feature that I want to talk about is known as ReLU nonlinearity. ReLU basically means rectified linear units. So sigmoid and tanh activation functions are much slower than this ReLU activation function during gradient descent. Basically uses the formula the max of 0 and x being the input. And we can see this here, the basic ReLU graph, or the representation of that, is shown on the left. And then on the right here, we have an example of a leaky ReLU, which will basically compensate for any of the data loss that's shown on the left. Once again, that's a story for another day. For now, we're just going to focus on these ReLU activation functions. So basically what this means is during gradient descent, the ReLU activation function was able to reach convergence about 6 times faster than using any other activation function, which is great because with these large sets of data we're going to be training, and the training is going to take a long time. So anything to reduce that time is really important, and that's why these ReLU activation functions are great to use. So the next key feature, we're just going to kind of keep on listing these off on rapid fire basically, was training on multiple GPUs. Now GPUs are very important for machine learning, as the data that we're processing is kind of stored in matrices, which is actually the same way that graphics are stored. So this is why a graphic processing unit, which is made to process these graphics, have a lot of the same operations that can kind of work on both. Thus, for all of these machine learning related calculations, we're going to start using GPUs. So basically, using multiple GPUs was able to speed up calculations really quick. As we can see here, they used a GTX 580 GPU, which only had 3 gigabytes of memory. This was a little while ago, and you can only imagine how today, as graphics cards become increasingly more powerful for lower amount of money, so better for cheaper, we'll be able to get even more and more power out of them. For example, on my computer alone, I have an RX 570, which just kind of shows that even as an individual, I'm able to have a more powerful GPU than that. So you can just imagine what some of these labs must be using. Another interesting aspect of this is that the amount of communication allowed between each GPU is another hyperparameter, as it was controlled by those basically running the experiments. So this can affect the efficiency and speed of training in the long run. So a very important hyperparameter there. So on to the next feature of this paper that I want to talk about is overlap pooling. So overlap pooling is similar to a max pooling or an average pooling operation. Basically, it's a layer that we insert into our architecture, and I found a video by SimplyLearn, which I'll link in the description, that gives a pretty good description of them. They're able to identify features such as edges, corners, bodies, eyes, etc. as they're trained. So the only difference is it's said in the paper that the overlap pooling reduces overfitting of the model, as it will summarize groups of neurons in the same kernel map. Basically, these operations will give its passing layer in their architecture a nice summary of the important parts of the images that this layer has input. So by overlapping, we basically mean that the size of the grid of the pooling filter is larger than the area devoted to each pool operation. So that means that some pixels may end up in multiple pooling operations. So overall, this is used to reduce overfitting of the model, as each data point will contribute to more than one kind of neighborhood in the feature map. So moving on to the next one, this is titled just reducing overfitting, which is kind of the main point of this video. So we're going to cover the next few points that they make, which includes data augmentation. So the whole point, it seems, of data augmentation is that you can kind of manipulate the data so that it can either turn into more data than what you actually have, which is important for smaller data sets. You can take out features that might cause overfitting in the model, or you can transform the images so you will have more training data. Basically, all of those three things are kind of summarized in this data augmentation section. Another interesting thing is that this is all done on the computer's CPU, while the calculations were done in the GPU, which allows it to not contribute to the time complexity of the algorithm, making it essentially free. So one technique they used was taking multiple patches from each image in the dataset and then training the network using those patches. So this gives the network more data to train, which will ultimately reduce overfitting, as it contributes a lot more data to the actual training of the model. Another form of data augmentation that occurred was that there was manipulation of the colors of the input images, so that the network could train with a variety of colors of the image. So that the network would train with a variety of versions of an image that had different colors. This one gives the network more data to train on, as listed before, but it also reduces the chances of the network being trained to recognize color patterns in images, which will overall contribute to the reduction of overfitting the model. And as promised, here is a little segment on the dropout section. Now, personally, I find dropout very interesting. It's a pretty cool effect that seems a little bit counterintuitive, but makes a big difference during training. So the basic idea of dropout is that we're going to set a few neurons in the network during each iteration of training to 0, basically meaning that they'll have no contribution to the network. So although it seems kind of strange to turn off neurons in our network, one, this is only done in training, which is very important to remember, and two, this will cause neurons to no longer be able to rely on each other, and co-adaptations in the neurons within the network are reduced. And as stated in this paper on Dropout, from the same team that brought us the current paper with the addition of Srivastava and Salakhutdinov, sorry if I butcher any of those names, called Dropout, a simple way to prevent neural networks from overfitting. These co-adaptations lead to overfitting as their neurons do not generalize to unseen data, rather double down on learning what is currently presented to them in training. So if you train, for example, with an image of a wolf, the model may learn to recognize very complex features of a wolf through multiple neurons, which is good, until we use the input image image of a butterfly, as it will have no clue what it is looking at. So to kind of combat these very complex but very specific relationships in neurons, we shut some of them off so they can't develop that level of a relationship. And although they'll learn less complex patterns, there'll be more general features. So yeah, this causes the models and neurons to learn more robust features, which will ultimately be better while inputting a large number of random input images during the testing phases. So that's all I have to say about the features in the AlexNet model that I thought were interesting and kind of contributed to the reduction of overfitting the model. I think it's super interesting how this model was able to do so much for the current climate of CNNs, especially how it was able to offer so many techniques to, like I said, combat overfitting. The results basically summarize how this specific model was able to destroy a bunch of other models in the competitions, and by that I mean it generally just had a higher classification accuracy. If you want to check out the specific results or anything specifically from what I said from this paper, as always, I've included the citations of the paper and the Dropout paper down below in the description. This concludes my talk about the AlexNet paper. I tried to talk about what I found interesting about this paper, and I hope you guys learned something from it. If you have any questions, or if there's anything that you feel that I've missed, or if I got something wrong, please feel free to comment that all down below, and I'll get back to you on that. So that's all for today. Thanks for watching. See you tomorrow.